Hello, everyone. Welcome. My name is Zhuang. I am a gRPC Java maintainer, and today, as Kevin mentioned, I will walk you through an overview of gRPC as an introduction. First, a bit of a trivia question. Does anyone know what gRPC stands for? Actually, gRPC remote procedure call is a correct answer. And remote procedure call is that you can execute a call function that execute in a different process or even on a different machine over the internet. But that is not the only correct answer. Actually, G can literally stand for anything, as you can discover in gRPC C++ main repo that is released every 6 weeks. And golden retriever pancakes, named after our mascot, is also a correct answer. But unfortunately, the nice-looking Google remote procedure call is not accepted. Okay, now let's have an overview of gRPC. gRPC is a general purpose. It can be run on different operating systems like Android, Linux, Windows. It can be run on different platforms like x86, ARM, and it can be run on the cloud, on your web, or on your mobile devices. It is language agnostic. We now support C++, Go, Java, Python, Ruby, C#, just to name a few. And the core part of that is that it can communicate in a mixed language environment between client and server. So that is really the core essence of gRPC. gRPC has tons of features to make your communication efficient and safe. For example, streaming, high performance, security, and stats tracing. And when I'm thinking of the most common use cases of gRPC, I'm thinking it's really like a very powerful modern smartphone. So you can do asynchronous unary calls. That is just like email. And you can do like streaming calls, just like a video chat. And when you send a single message out to your mom, she might reply with 10 messages. That is a server streaming call. gRPC is secure. We have different ways to do credentials to do the authentication, just as you can use fingerprints or Face ID to log in. And gRPC has a strong native support for observability that keep tracks of your RPCs within stats and tracing, for example. And that is like your smartphone is keep tracking of your activities, like screen times. The feature list goes on. So you can really rely on gRPC as you rely on your powerful smartphones. This features makes gRPC excellent for building microservices. Now let's have an architecture overview, as well as familiar with those terminologies, have a refresh on it before we dive in deeper into more technical details. So the outermost layer of the framework that closest to the application is called a stub. Stub is a convenience that gRPC provides to the users to build your application. It's very quick, it is easy and cheap. It is also really closely related to the protobuf generated code, and we can talk a bit more about protobuf later on. The next layer that the stub layer built on is the API layer. So when you're using stub, you're actually indirectly using API, but you can also directly use API layers to get around the stubs. That gives you some powers, because some of our APIs, they're only exposed at API level. Some of our features only exposed at API level instead of the stubs. For example, you can do flow controls on the API level. And channel is probably the most important concept here at the API level. Channel is conceptually an endpoint that you can send and receive message to. It is not a connection though. Instead, a channel manages multiple connections and then they can multiplex RPCs on it. Sometimes in the API level, we corresponds to a RPC as a call. This is also terminology. The next layer of the framework is the core part. So there are many interesting subcomponents in the core that an RPC will experience in its life cycle. The first thing is the name resolver. So the name resolver's job is to find where the backend is and how to connect to it. It is pluggable. Next component is the load balancer. Load balancer's job is to manage the connections. Here, the connections, we call it subchannels. And its job is also to find which RPC to go to which subchannel. A load balancer is also pluggable. Buffering and retry is also in this layer. So buffering is that when you start request, gRPC not necessarily immediately send out to the wire. Instead, it might queue it internally because it needs to fetch other informations to put things together, and then it will send out. Retry is that if your previous attempt failed, for example, and then gRPC will automatically do a replay of your messages on the transport layer, hoping that it will be successful for the second time. That will increase your communications robustness. Some of the security stuff is also in the core layer. For example, the gRPC might be fetched some tokens before it is able to establish communication or start an RPC. The next layer is called transport. The transport is kind of invisible to you, but it's important. It is just a lot of heavy liftings to put your bytes into the wire. gRPC has many different kinds of like transports for different use cases. Like if you're developing on Android, you might use an OpenHTTP transport. If you are doing testing, you might find the in-process transport to be useful. And maybe in prod, you're using the NetT transport layer. And all those, they are compatible with the API and the core part of the API, core part interfaces. And gRPC, the transport is compatible with HTTP2 protocol. That is important to make it high efficient. We can also talk about more later on. And here, interceptors is interesting and a concept. It's kind of API layer, but it really gives you the power to rewrite your channel and a call. And sometimes gRPC will expose its APIs through interceptors. For example, OSI is one use case of that. And people also use interceptors for logging purpose, etc. So as you can see, gRPC is really versatile in terms of how it's providing you with the building bricks to build your application. So we just mentioned that gRPC is built on 2 community standards. The transport layer is built on HTTP2, and there's also protobuf. HTTP2 is an IETF standard. It is derived from the early speedy experimental APIs that originally developed by Google. It makes it, gRPC using HTTP2 really makes it compatible with load balancers and proxies over there in the wild internet. HTTP2 reduces the number of TCP connections. It is binary. It includes header compression. All of these features make our gRPC very high performance, reduce latency, and make better use of your resources. So protobuf is an open source project that does the data serialization. There are 2 major parts in protobuf. One is the protobuf file that is written, that you write the IDL interface definition language to write a contract between your client and server. And the second part is the proto-C compiler. So the compiler is written in C++, and it has 2 major parts. It generates your code, and it has major 2 parts. One is built-in, the other is plugged-in. The proto-C compiler built-in, it natively supports generating different languages for runtime libraries like C++, Java, Go, etc. And the other plugin is an extension to the proto-C compiler that can pass and decorate your generated code. And internally in gRPC, we have a custom, like kind of a plugin. That is how like gRPC will turn your proto file into the stubs related things for you to easily run your applications. Those concept lectures kind of boring, so let's entertain ourselves by looking at some code. So the first assignment here you see is that I create a channel object. By providing a target string. The target string is used for name resolver. I also provide the credentials I need here for simplicity. For test is insecure. And then I will install interceptor that will go through the business logic for every of your RPCs. This is the API level concept. And then I will supply this channel towards the generated code to return a stub. And then I will do a blocking unary call here. So the blocking unary call as a stub will block your call until you get a response. So this is quite simple. Actually, underneath, gRPC is always asynchronous, but the stub layer gives you some sugar to do unary style or streaming style calls. For example, the next example is actually a streaming call. that you create a asynchronous stub this time, and you will provide a request to send out and also a stream observer. So the stream observer is that you kind of provide a callback for a gRPCs to receive those messages later on when it receives from the server. Here, the callback, the gRPC will call your on next when it receives response, or call on complete when the RPC finishes, and call on error if there are exceptions. So now we have more lectures. So let's break down the client part component, the manager channel components, to have a better view of the gRPC architecture. Here, as you remember from the code snips, we just constructed a channel from a target string. And this target string actually looks probably very familiar to you. To give you a refresh, the URI, standard URI, the syntax is it has a schema like HTTPS, and then colon / authority / path. And gRPC follows this standard. However, it has its own interpretation of what the target URI means. And the schema, for example, is actually specifies the name resolver to use. And internally in gRPC, it has a map between the name resolver name and the provider of it. And when you specify it, when you're creating the channel, gRPC will plug in that lazily for you. So that is how gRPC make your name resolver pluggable. While the authority and the path part may have different meanings depending on what the particular name resolver is. For example, in a DNS name resolver, which is the by default one, it will be a DNS server that you communicate with to resolve the host names that you can connect it to as a backend. And when, for example, the schema is an XDS, then it's completely different. The authority part can be the control plane. So TLDR XDS is a gigantic name resolver and load balancer. So the next component is that the result of name resolver. So traditionally, when you use a URI, you are trying to discover resource, right? And the resource, in the point of view of gRPC, is actually resolved to address and service config. Service config can be very powerful. It is JSON map, and the most important part maybe in service config is that it specifies which load balancer you use, and that is also how gRPC make the load balancer pluggable. There's an internal map between the name of the load balancer and then the instance of it. And when we receive a service config specifying which the load balancer to use, it will just plug in to do its client-side load balancing. And the load balancer manages connections. Actually, we call subchannels here. To decouple the different systems together, actually, the load balancer will return a picker to the channel. And then when there's an RPC, the channel will decide which transport, which subchannel to connect to by calling picker.pick. So this is kind of the architecture of how things is happening. The subchannel is conceptually the HTTP2 connection, but we can talk more. The server side, as compared to the client side, is thinner. There are two types of sockets. The listening socket is always waiting for connection, and then once it is accepted, it will quickly hand over, create another socket, child socket, to do the real connection. And this connection is what the client side load balancer creates and manages too. So we mentioned that gRPC is built on HTTP2. That is important. And I think it's worthwhile to have an overview of the mapping between HTTP2 concept and gRPC, because I think it is helpful when you're running your application and doing some debugs and see RPC level of failures, or you're adopting some new features of gRPC. So we mentioned that gRPC channel manages a bunch of subchannels. That conceptually is a HTTP2 connection. And then when we're doing RPCs, we actually schedule those RPCs on those connections. And just as the mapping between a subchannel to a connection, here an RPC is mapped to a stream at the HTTP2 world of concept. In HTTP2, a connection can have multiple streams, and then those streams are delivered onto different frames. And gRPC wraps itself onto those frames. Visually, it's like this. So when the gRPC client sends message to the server, it has headers and payloads, right? Here, for simplicity, we only include data header and data frames. So what happens is that gRPC will send its metadata over the HTTP2 header and the continuous frames. The header part, gRPC will combine your application's header together with gRPC's headers and throw it together. For example, the path header in HTTP2 is actually corresponds to the server's name and method name in gRPC. So the payload are delivered in HTTP2 data frames. The data frames has its own like fields for like length, flags, and payload. gRPC wraps itself in this HTTP2 data frames and has its own syntax. Here it has the compressed flag, the message length, and also the message itself. To be clear, there's no strict relation in terms of the boundaries of these two types of things. So the gRPC will handle that. And finally, when the request ends, we will send a data frame also with a flag set, the end of stream flag set to indicate that stream is over. At server side, similarly, we use HTTP2 frames to convey the responses. And a little bit difference is that in the response side, you have response header and the trailer metadata, plus the response data in between. And normally we have both header and trailer, but trailer metadata only messages are available, permitted actually, if say you want to immediately close RPC with only the status code. And in the trailer metadata, we will include the gRPC status there, which is a protocol, it is a must. And as for the mapping between HTTP2's status code and gRPCs, we can find in this short link in the bottom right. That actually concludes my overview of gRPC. There are some useful links here. Highly recommend the YouTube channels. There are some recent interesting stuff there. Yeah, thank you, everyone.
Does anyone have any questions for Ivy? Yeah.
This one.
Yeah, this one. So you have a name resolver. Let's assume that I'm using XTS. Now, the client is going to have behind it XTS. You have multiple pods running. Right? So, and each pod has its own services deployed. Now, the name resolver is it going to have all the channels connected to the client side?
Nope.
Meaning like the client is keeping all the client all the server connections in the client side, so that any request comes in, passes through at some time at load balance sites, or is it making only one connection?
Oh, this really depends on your algorithm in load balancer. So for example, in gRPC, there are some built-in load balancers like pick first. Even though there are many backends, it's only used the first usable one. And if it is round robin, then it will make all of the connections and then select one by one.
I mean, all of the servers. So if you have 100 pods running, it makes connections to all 100 pods?
I believe so. It keeps the connection open. If that is your name, what your load balancer does. Sometimes it does this. So gRPC sometimes in high scalable systems, there are thousands of connections open. It's possible. Yeah.